So, ladies and gentlemen, welcome to the webinar LED Luminaire Design, Optimization and Analysis, sponsored and presented by Lambda Research and organized by LED Professional. I'm Siegfried Luger, publisher of LED Professional. Mr. Dave Jacobson, Senior Application Engineer at Lambda Research, will present this webinar. At the end of the webinar, Dave will answer also your questions in a Q&A session. Please use the chat field within your webinar control panel for this function at any time. Now, let's get started. Dave, over to you to present the webinar, please.
Thank you, Siegfried. Hello, everybody. Thank you for attending our webinar today. Also, thank you to Siegfried and LED Professional Magazine for sponsoring this. Our webinar today is going to be on LED luminaire design, and we're mainly going to be looking at optimization and analysis. What I'm hoping to show today is sort of an easy, using some of the software tools that are available, how you can easily go through this process, as well as also showing maybe some ways of using an optimizer that you might not have thought of in the past. So to start off, as Siegfried mentioned, my name's Dave Jacobson. I'm the Senior Application Engineer here at Lambda Research. I've been here for a little over 5 years. Prior to that, I was working with PerkinElmer, formerly EG&G, as an optical engineer, doing a lot of work with xenon light sources and xenon light source applications, spectroscopy systems, machine vision, things like that. Here at Lambda Research, we're celebrating our 21st year in business, and we're the makers of TracePro, the TracePro bridge for SolidWorks, and the Oslo optical design and analysis software. And as Siegfried mentioned, as we go along, if there are any questions you have, please feel free to enter those in that question or chat dialog box, and we'll address all the questions at the end of the webinar. So our agenda for today is we're going to look at designing LED lighting systems using SolidWorks and then the TracePro bridge for SolidWorks. We'll look at using the information from an LED datasheet to make a surface source property based on that, based on the spectrum and the angular distribution. We'll talk about setting up and defining a 3D model for analysis and optimization. We'll touch a bit on some different types of optimization methods. And then we're going to look at a reflector optimization and a diffuser optimization and see how those are different and how you set things up differently based on the results you're looking for. Then also we're going to touch on creating IES files. This would also be applicable to IllumDat or LDT files, since I'm assuming most of the attendees here today are in the lighting industry. So we'll show how you can create IES and or LDT files based on the ray trace results. And last, I'll just show some photorealistic rendering results of the design that we'll go through here in today's webinar. This is just an overview or the model that we're going to be looking at. And what we're going to do, or the goal today, is to design and optimize an LED reflector and diffuser combination. In this case, we have a small luminaire here. We have an LED array that we're going to use as our source. And we have a target placed 1 meter away, and this target is approximately 1 by 1 meter. And we're going to look to produce a specified uniformity pattern, specified irradiance or luminance pattern across that target. And we're going to use the tools available to us to do that. Okay, to start, just to kind of show a typical workflow in the way I normally see it. as far as the LED luminaire design process. And like most designs, it's going to start off with a project specification or a design goal. And this could be a back and forth type document between a customer. Customer could be internal or external, could be a vendor. Basically, it's going to set forth what are you trying to do, what are you trying to produce. Next step would be calculating source requirements. What type of an LED do we need? How many of them? Is it a white LED, monochromatic? Once you've defined that, you can look to choose the source. And once you've done that, you can start to get ready for doing the optical analysis, the optical design. First step I usually do is I model the source. Or if it's available, I'll get a ray file. Ray files, for people that may not have used them, are a file where the manufacturer has taken their LED. Now, I'll just mention LEDs in this case, but it's really applicable to all sources. But they've had it measured, and they've saved all that data, and they've produced this ray file, where each line of the ray file represents a single ray. And each ray will then have an XYZ starting position, direction vectors, and flux values. So what's nice is it's a complete representation of the source. It takes into account any of the geometry, the materials, the surface properties. So you don't necessarily have to go and build a complete 3D model of the source. Once you've done that, then we can look at setting up the initial model. In this case, I have setting up in the Optimizer. Then we could look to set the model up in this case, TracePro. And this would include the optic, the source, and the target. We then define our optimization goals and targets. What are we optimizing to? What is our goal? Then we'd run the optimization process. Once we've done that, we can analyze the results. I'll show you some of the tools that are useful for that today. We could then output the design, whether it's CAD files, drawings, IES files. This next step may or may not be done in-house, but fabricate a prototype, measure that prototype, and see if it meets the design goals. And then, if necessary, update or make any changes. And finally, deliver to the customer. So we're going to show today sort of how we can go through some of this process and some of the tools that are available, and really how easy it is to get started and get moving with it. Now, the first step is going to be modeling the light source. In this case, I picked, it's a Seoul Semiconductor 13-watt LED array. And basically, I picked this one because I actually saw a picture of it in a previous issue of LED Professional magazine, and thought it might make for an interesting model. It's not one that I've worked with in the past before. I should also mention, I'm going to use this as an example, but really you can use any LED or light source you want for this process, as long as it's going to meet your requirements. On this light source, I looked for a ray file, but I wasn't able to find one. So I took a step back and I made a 3D model of the source. In this case, I used SolidWorks to do my geometry. Here's my resulting SolidWorks model. I'm not going to build that live during this part of the webinar. I'm not that good with SolidWorks. But then what I want to do is I'm going to use what we call the TracePro bridge for SolidWorks to apply the optical properties to the model. And this is a plug-in or an add-in to SolidWorks that lets you apply optical properties such as surface properties, material properties, or in this case, what we call a surface source property. And this surface source property is going to have the angular and spectral distribution of this LED. And I'll show you here in a few minutes how we actually make that surface source property. Once we've applied the properties, we can then export the model directly from SolidWorks to TracePro for analysis. The advantage of doing it this way is all of these properties are saved as part of the SolidWorks model, so you don't need to reapply them when you bring the model in for analysis. So what I'd like to do now is exit out of the presentation here and show a quick demo of how easy it is to apply these properties in SolidWorks. And I already have my model open here in SolidWorks. And what I'm going to do is I'm going to select the emitting surface of some of these chips here. Get my mouse over here. So I won't do them all, but we can go through select all of them. And I'm just going to do a right click. And, oops. Try that again. Sorry, right click and then choose Edit Surface Source. And this is part of the features that are added in to SolidWorks with the TracePro bridge. And I'm going to move this divider here so I can see a little better. I'm going to pick a source property. It's from the Seoul Semiconductor catalog. And I'm going to pick that 13-watt array. And as I mentioned, I'll show in a few minutes how we actually create this property. I'm going to leave my total rays here. I'm going to trace 10,000 rays from each of these surfaces. There's 30 LED chips here on this array. And I'm going to set up my wavelengths. I'm going to use a feature called Calculated Wavelengths. And I'm going to go from 0.4 microns, 400 nanometers, to 0.75 microns, 750 nanometers. And I'm going to use, in this dialog where it says pound include or number sign include, 10 wavelengths. And that's going to put in, oops. I'm going to put in 10 wavelengths within that band. And I can accept that. And now if I'd gone through, if I selected all of these, it'll apply all of those properties to this. I could also go in and apply other properties, such as a surface property for like a diffuse white for the body or the material of the die here, or the mounting package. But from there, I can then go and do a file, save as, and one of my options for my save as type is a TracePro file, star.oml. I can then export that file right over to TracePro. And going back here, just opening up a copy of TracePro. Here's that same model. I exported it. I added some color to the model just to show the phosphor surface, basically just to make it appear a little bit better on the screen. But if I was to select one of these surfaces here, I could see here's that Seoul Semiconductor property with 10,000 rays applied to it. So very easy to do your model there. And then once you bring it into TracePro, it's ready to start using as part of the analysis. And just a screenshot showing that what I just showed in the software. Now the next step, and this sort of predates that first step, but if we want to make a surface source property for this LED, if it was one that wasn't in some of the preloaded catalogs, and in this case it was not, I can start with the datasheet. And here's the datasheet for this, just downloaded right from the Seoul Semiconductor website. And there's 3 bits of information I want to use in this case. One is the lumens output of the LED. In this case, it's 1,000 lumens. I have my spectral distribution, and I have the angular distribution, the beam pattern. And we're going to use those 3 pieces of information to make the property. And we're going to do this using a utility that we include with TracePro. It's called the Surface Source Property Generator utility. And it allows us to cut and paste the graphs from that data sheet into this utility, and then just click along the curves and trace them, and then produce the properties from there. And again, I'm going to jump out. I'll show a quick demo of how easy that process really is. I'm going to go here to my utilities and then surface source property generator. And here I have the data sheet for the LED. As I mentioned, I'm going to use 1,000 lumens as the output, which is the typical flux for this package. And I'm going to scroll down until I find the, here it is. I'm going to use the neutral white spectral distribution here. And I'm just going to use an application. I'm just going to copy it to the Windows clipboard. I'm going to go back to my utility. I'm going to paste that graph in. And the first step is to just define the limits of this graph. And it goes from 0.3 microns to 0.8 microns, and from 0, we'll use 1 here. So I'm just going to set these reference points here in the corners. And now I can just click along this curve, and hopefully it's visible through the webcast, but you'll see that the utility is fitting a curve, and I'll draw a line out there just to exaggerate it. But the utility is fitting a curve between these points. And we do that, and we add enough points to accurately trace that spectrum. And I can increase my number of sampling points. I can look over here. I can see it's giving a reference CCT, correlated color temperature, of about 3,850 Kelvin and a color rendering index of about 82.5. I can then repeat the process, go back to my data sheet, and let me find the angular distribution. There it is. Or is it called here luminous flux characteristics. Once again, copy it to the clipboard. We can paste that into the utility. And it's the same procedure. Define the limits of the graph, 0, 0 for the origin, 1 or 100% along the 0 degree, and then just a point along the 90-degree axis. And again, a few clicks of the mouse, we can trace that curve and get the angular distribution. And in this utility, we're not limited to just asymmetric profiles. I mean symmetric profiles. We could also define additional azimuth angles. So if the source had an asymmetric distribution, we can add those additional angles and profiles and produce the source that way. And then the last step is giving it a name, a catalog name, and a property name, and setting up, defining the flux. In this case, I'm going to have lumens. And this array had 30 LED chips, and there was 1,000 lumens. So it's 33.33 lumens per chip, approximately. So that's what I'm going to set it up, because I'm going to apply it to each one of those 30 surfaces. So when they're totaled up, they'll produce the 1,000 lumens. And then we just export the property to the software, and then it'll be saved as part of the database and can be used at any time in the future to in any models. Let's go back to our presentation here. So those steps were sort of the preliminary work that's usually done when you're starting this process. We're defining our source, applying our properties. And here's the system as we set it up for analysis and optimization. I've added a target surface. I mentioned earlier it's 1 meter away, and it's roughly 1 meter by 1 meter. And that's what I'm going to use to collect my light. That'll be where I'll do my analysis, look at my irradiance profiles, or in this case, illuminance profiles. A little bit of a close-up of the reflector. The reflector in this case, it's 100 millimeters in diameter. It's 150 millimeters long. I picture this as sort of a pendant luminaire that might hang down over a desktop or over a bench or a countertop. And then here's my LED array in the background that I've imported the SolidWorks model. One thing I've done here is on my initial reflector, I've applied a surface property to it. In this case, I chose Alinod Miro 27, fairly specular reflective material, and all the examples going forward are going to use that same surface property for any calculations. But here's the initial results. This is an illuminance map on the target surface. We can see here it's actually presented right on the surface in the model. But we can also look at it in a separate window. And in this case, I'm looking also at the profiles. In here, I can see I have a very hot spot, a bright spot, right in the center. And that's what I want to try to minimize. This aesthetically, this would not be what you'd want to have, I think. You don't want a very bright spot right in the center of your lighting pattern. So the goal then for today is we're going to try to optimize this and improve this result. Now, usually when I do presentations like this, I don't like to have slides with a whole lot of words on them. So I apologize for this one slide. This will be the only one that is like this in the webinar. But we have, in this case, two optimization methods that we can choose from. And we're actually going to use both of these in the webinar today. The first one is the downhill simplex method, also called Nelder-Mead, after the two gentlemen that originally proposed this method. And this is a local optimizer. And that means it's going to converge to the solution closest to the starting point. It also means it's possible that there's a better solution somewhere there in that solution space. And a useful test of that is to just change the starting conditions and then see if it optimizes to a better solution. This type of optimization method is a good choice when you're optimizing parameters such as geometry, position, and rotation, where it's desirable to jump around that solution space to find and then refine the best choices for variables. The second method is what's called variable scanning. And the variable scanning method is used to step or scan through all possible variable combinations. You could use this as a method to define a range of variables that could be then fed into the downhill simplex optimization. Or, as we're going to use it today, we can use it to step through a catalog of properties, in this case diffuser properties, to find out what's going to be the best solution for that problem. So here's a simplified graph of the solution space, and we're going to look at how the downhill simplex method would find a solution. I'm going to turn a pen on here so I can draw on my screen. So this graph here, or this grid, covers the range of possible solutions for a particular problem. It's not specifically this one. And where we see these dips, well, those are our local minima. Those are our possible solutions. And which one of these we're going to find is going to depend on where we start. If we start our model over here, we're going to tend to fall into this solution. And if we start here, it's going to come down here. Now those are solutions, but they're not necessarily the best one. In this case, this here is our best solution. So for example, if we started here, then we'll tend to fall into that or optimized to that solution. So this is why it's an advantage to sometimes try multiple starting conditions for your model, just to see if they all produce the same results, or you may find a better result. I'll show an example of that too shortly. The variable scanning method is we're going to use it, or the way we're going to use it today, is to step through all of these properties in this catalog. In this case, these are Mold-Tech profiles. These are textures that can be molded into plastic materials. In this case, we're going to make a diffuser out of these properties. So we have 7 options here within our catalog, and we're going to use the optimizer to pick the best possible one out of those properties. Just as a side note here for anybody that's interested in finding out more about LED luminaire design optimization, really the theory, methods, and applications, we'll be presenting a symposium at the LED Professional Symposium and Expo in Bregenz, Austria in late September, early October. So anybody that's interested in finding out some more of the details about how these optimizations are performed, what happens in the background, and how you can improve your results, we're welcome to have you at that presentation. So now let's take a look at actually optimizing the reflector. We're going to start, as I mentioned, my base luminaire. It's 100 millimeters in diameter. It's 150 millimeters long, and I have one control point here. It's a simple spline surface between the vertex and the end of the reflector. So one spline control point, and this dashed box here, let me highlight that, is the range of motion of that variable. So this variable can move along anywhere within that bounding box. A lot of times you'll set the conditions of this bounding box. For example, we don't want it to have this line cross the center, or we'll have intersecting geometry. We may want to control the movement of one of these points so that the luminaire does not get too large or too small. Also, I applied the surface property I mentioned previously. This is Alinod Miro 27, so that's the reflective surface of the luminaire. Turn the pen off. Now the next step is setting up my targets. In this case, we're going to have 2 optimization goals. So the first is an irradiance profile. And here's that profile here. It's along the surface that I called target previously in the model. And we want to have a relatively flat profile across the center and then tapering off towards the edges. As a secondary optimization target, I'm setting a flux value. I want to try to keep the flux as high as possible while still maintaining that profile. So a goal in this case was 750 lumens from the 1,000 lumens of the luminaire that was putting out from the LED, I should say. Now what I've done is I've actually made a video of the optimization process to speed it up for this presentation. But the way the process works is the optimizer sends over the model, the ray traces run in the software, the results are analyzed, they're compared to the target, the variable is moved, a new geometry is generated, sent over to the program, and the process continues to iterate that way. Also, we can see here I have the illuminance map from the model shown here in the lower left corner. I'm just going to let this run. And we can see initially how that point is jumping around inside that solution space. we have here in the lower right-hand corner a trend chart of the error function. So the lower the error function, the better the result. This red highlighted iteration of solution here is the best one it's found so far. I think this goes through about 60 or 65 iterations before it stops. But you can see now too, we're closing in. It's the moves, the changes in position are getting smaller and smaller. So it's finding a solution in this area. We can also see here in the trend chart that the values are staying about the same. They're not changing much. And you're able to, in the optimizer, to set end conditions. How do you want to end it? By number of iterations, by the limits to how small a change is from one iteration to the next. And this is just about done here. Okay. So it found the best solution, in this case, at the 60-second iteration. We could see really after about 20 or 30 iterations, it was within the ballpark, we should say, of the solution. And then here's our results after that reflector optimization. We've spread the beam out. We've got more of a flat top sort of profile in the center. But we do have this structure showing up here. And also, I looked at this, I saw these sort of spikes here that correspond to this bright ring around the illuminance pattern. So my next step was to see, could I use a diffuser to change that? And before we go to that, here's the before and after. So we have smoothed that out quite a bit. My initial flux was about 640 lumens. I've actually increased the flux to about almost 660. So we smoothed out the profile without losing lumens. So that was good. But I still want to see, can we do better? But before I get to that, I wanted to mention, or I mentioned changing the starting condition. And in this case, I moved my variable point up to the upper right-hand corner of the variable range, reran the optimization, and compared the results. Here's the results after the first optimization, and here's the results with the second starting condition. In this case, the first condition better meets our goal, so I'm going to stick with that one and discard that second starting position. So just a way of testing our solution. It looks like we found probably the better solution this way compared to starting there. So for our next step, we want to look at using the optimizer to pick a property. In this case, a diffuser property. I made a simple diffuser here in the optimizer. It's just an acrylic disc, 100 millimeters in diameter. I think it was about 5 millimeters thick. And I'll apply the diffuser properties to one of the surfaces of this. And in this case, it's a molded diffuser property. And this is an option where I switch to that variable scanning method. And I define a variable. I'm calling it surface. It has a range from 1 to 7. If you remember previously, there's 7 properties in this catalog. So this is going to step through that variable from 1 to 7 in increment or in integer values. And then the last step is writing a small bit of macro code. In this case, it's only 4 lines long that applies that property to the correct surface and then moves through or iterates through the different property names and then refreshes the model each time. Once again, to save some time, I made a video of the process. And in this case, as I mentioned, we're not changing the geometry. We're happy with the geometry where it's at. We're just now looking at the results for different diffuser profiles. And I'm going to run this one here. And we can see the illuminance pattern here changing, as well as the error function moving around as it goes through these different profiles. And after the optimization is finished, it's saying here that solution highlighted in red, it's the property, the third property. In this case, it was Moltec_3. So I applied that property to the model and reran the ray trace. A couple things to notice here. Those little spikes are pretty much minimized there. We have a much smoother profile across the center. We don't see all that structure. So adding the diffuser has improved the results. And here we see the side-by-side. Here's after the reflector optimization, so no diffuser. And here's the results of adding the diffuser. We did lose a little bit of lumens from 65 or 66, or sorry, 656 lumens down to about 587. So we lost a little bit of light, but we have losses through the diffuser. We have additional scattering and spreading of the light, so, but not too bad. And then our starting condition compared to our final condition. Here was our bright spot in the center, and then here's our final result, our illuminance here with a much smoother profile, probably a more aesthetic looking light, better, more uniform, more pleasing to the eye. I just want to quickly touch on a couple other points here before we start wrapping it up for today. In that previous example, I used a catalog of profiles that was already loaded in the software. Another option is to make your own catalog of arbitrary values. And that's what I did here. I made a catalog of diffusers that had diffusion angles of Gaussian half angles for the diffusers from 1 to 10 degrees. And these are just plots of that angular spread normalized to 1. And I wanted to see, out of these properties, which produced the best result. And I won't run through a video here, but I just show the final results. Here's our optimization log and trend chart. And basically, in this case, an 8-degree Gaussian half angle produced the best results. So I could then take that information and now find somebody who's producing a diffuser like that or have a diffuser like that made. So we could use this optimization process to also generate a specification that we could then send out to have a diffuser designed or purchased. Now, in addition, there's numerous other or additional parameters that are open to optimization, not limited to just geometry or catalogs like this. We could look at position, thickness, rotational angle. We could scan through different reflector surface properties, changing reflectivity and scatter. Say I mentioned Alinod. If I wanted to scan through all the possible Alinod materials for reflector materials, I could set the optimizer up to do that. We could also look at changing the diffuser material property. Is it acrylic, polycarbonate, PMMA? See what effects those might have. So these are all things that you can optimize using this type of an optimizer. To sort of start wrapping this up here, I mentioned earlier IES files. Well, we could take this Luminaire with our diffuser in place. We can run the ray trace. We can generate a candela plot or an intensity plot. And then we can use that to create either an IES or an LDT file that you could then send to another program, whether it's Oxytec's Lightstar 4D or Dialux or AGI 32, architectural lighting programs where you can now take this IES file from this Luminaire and insert it into a model environment where you might be modeling the furniture, the wall finishes, the carpeting, and to see how it performs there. So this is capabilities we have as well. We also have, that we include with TracePro, is an IES LDT analysis utility that would allow us to use that IES file to create custom lighting reports. And here's just a few samples of some of the graphs that are possible. These are some of the default reports that are already predefined, but we also have the ability to create custom reports where you can drag the analysis tools that you want to see into the report and then customize it for your own application. And then as a last step, sometimes a diffuser is not used just as a way of spreading the light out on the surface. Diffuser can also be used to hide sort of that high luminance point source like nature of the LEDs. In this case, I'm showing it's a photorealistic rendering here. Here's the reflector without the diffuser. We can actually see a reflection of the LED chip. I angled the reflector in this case so it blocks direct light from the LED, but we're seeing reflections off the reflective and shiny surface inside the Luminaire. So this could be glare, it could be something that's just not pleasant to look at. And here's the same orientation, same reflector, but now when we add the diffuser, so we see a more uniform source of light, a little more pleasing, not quite as aesthetically jarring to the eye. So with that, I'd like to sort of just summarize quickly. What I've hoped to show today with TracePro is that you can streamline that illumination design process and accelerate that time to market. Some of the features that we like to promote for that, it's a familiar CAD interface, as well as the TracePro bridge for SolidWorks, superior ray tracing performance. We have a large number of tools and utilities that are optimized for the lighting and Luminaire designer. We'd also have comprehensive visualization and analysis tools, as well as the 2D and 3D optimizers. Everything I showed here using the using our 3D optimizer. I'd also like to invite anybody that might have their interest tweaked by this webinar. We do offer free 30-day trials of our software, and you're welcome to sign up at our website. It's linked there, as well as our phone number and email. And also, if you have any questions about this webinar, please feel free to contact me. My email address is djacobsen@lambdares.com. So it's djacobsen@lambdares.com. And I'd certainly be happy to talk with anybody about what we've presented here. And I think with that, start looking at some of our questions and answers.
Thank you very much, Dave, for this very interesting presentation. There are some questions. For example, if you can use the ray files to model the LED output, or
you can. We have full support of ray files, both monochromatic and polychromatic, or multicolor. In this case, I mentioned earlier, a lot of times I will use a ray file for this type of an application, but in this case, there wasn't one available. At this point, either it hasn't been published or the measurement has not been made. So I went and I used the surface source property that we have. But yes, you could use ray files quite easily for the optimization.
We've just seen that there's a question from one of the other attendees, and he asks, What shape is the reflector? Is this a parabolic design?
It's not strictly a parabolic. It's close. It's a spline curve with that one control point on it. Its starting point was probably relatively close to a parabola, but I wouldn't say it's exactly a parabola. It's sort of a free-form curve.
Okay. Let me please come back to the array files. I think you had 10,000 arrays for the tracing here now. Is that correct?
In this case, it was 10,000 rays per chip or per LED emitter. Yeah. So it's 10,000 times 30.
Do you recommend a certain range to stay within? What does make sense?
It really is going to depend on looking at the results. Let me just go back here a slide or two. What I look at is the results I see on my, in this case, an illuminance map, and do I have a smooth profile? Do I have enough rays that, you know, I have a good signal to noise ratio? And I mean, I usually, with an array like this, I would say, you know, I'd want to have at least a couple million rays coming off of that. In this case, I have almost 120 million rays hitting the target. So.
Okay. Another question from the audience is it possible to make facets on reflector surfaces?
It is. We can have facets both in the radial and the azimuth, or in the polar angles, so we can do a faceted reflector. We've also just added in the capability to do curved facets, and that'll be in the next release of the software. So that's a new capability we're adding as well. So currently we can do a flat facet, but look in the very near future for the ability to do curved facets as well.
Great. I see another question from the audience. In an optimization session, do you have a capability to export a CAD file?
Well, what winds up happening is you export the file from the optimizer to TracePro, and then from TracePro you can save the file as an SAT file, or with optional translators, a STEP or an IGES file. So you can generate that 3D solid CAD file from TracePro. So you just send the geometry from the optimizer to TracePro.
Okay. Yeah. What about optimizing both reflector and diffuser at the same time?
In this case, you would not be able to, because they're using those two different optimization methods, which is, one is using the downhill simplex method, the other is using that variable spanning. So in this case, you would not be able to do that. As a test, after I optimized the reflector and then optimized the reflector, I went back or optimized the reflector and then optimized the diffuser. I went back and then tried to re-optimize the reflector with that diffuser I found. And in this case, it made very little difference. So for a process like this, I tried to do as much with the reflector as possible and then add the diffuser.
Okay. So there is again a question from the audience. What's your method you use for the ray tracing? Is it FDTD or Monte Carlo method?
We use Monte Carlo for this.
Okay. So just before you mentioned that you are switching from the diffuser to the reflector optimization if you want to get to even better results, but it doesn't make much sense in this example. But what is in general, if you are doing it the other way around, starting with the diffuser and then doing the optimization of the reflector.
That could also be another, I didn't try that in this case myself, but that would probably be another way to try it as well. Might be interesting to see how that works, see if it produces a similar result. So you could go that way as well, have a starting reflector and then optimize the diffuser and then see if changing the reflector improves those results.
Okay, great.
Yeah, thank you, Dave. I think we are at the end of this webinar. Okay. And if there are open questions,